Isotope bromine 79 has an atomic mass of 78.9183 AMU, or atomic mass unit, and we're given the relative percent abundance for that isotope. Now we're also given the same information for isotope bromine 81. We have the atomic mass and the percent abundance. So with this information, how can we calculate the average atomic mass of the element bromine? So there's a formula that we could use. It's equal to the mass of the first isotope times its percentage as a decimal, plus the mass of the second isotope times its percentage. Now, if you have 3 isotopes, this can continue, or if you have 4, so it would be plus M3P3 plus M4P4. But we only have 2, so we can stop here. In this case, M1 is the mass of the first isotope, so that's going to be 78.9183. P1 is the percentage for that isotope. Now we need to convert it to a decimal number, and so we got to divide 50.69 by 100. So that's going to be 0.5069. Now the second mass is 80.9163. And now we need to multiply it by its percentage, which is 0.4931. So you can also move the decimal point 2 units to the left if you're dividing that number by 100. Now, let's plug these numbers into a calculator, and let's get the answer. So what I got is 79.90. And so this is the average atomic mass of the element bromine. And you could check this answer out. You can go to Google Images, look up the average atomic mass for bromine using a periodic table, and you should get about 79.9. And so that's how you can confirm your answer in this case. So that's it for this problem. Now you know how to calculate the average atomic mass of an element. Now let's move on to our second example. The average atomic mass of boron is 10.81 atomic mass units based on the stable isotopes B10 and B11. And we're given the mass of each of those stable isotopes. Part A. Calculate the relative percent abundance of each isotope. So in the last problem, we had the percent abundance of bromine 79 and bromine 81. It was about 50.69% and 49.31% respectively. In this problem, we need to calculate those relative percent abundances. So basically, we're working in reverse. Now we're going to use the same formula where the average atomic mass is equal to M1P1 plus M2P2, since we still have 2 isotopes we're dealing with. If you go to the periodic table, you should see this for boron. It has an atomic number of 5 and an average atomic mass of 10.81. Now it's important to understand that when you see this number, it represents not the mass of an individual isotope of boron, but rather the average mass of all the isotopes of boron on the Earth. So just keep that in mind. On the left side, we're going to plug in the average atomic mass, which is 10.81. The mass of the first isotope, we're going to say that M1 corresponds to B10 and M2P2 corresponds to B11. So the mass of the B10 isotope is given to us as 10.0129 times its percentage. Now, the percentage we don't know, so we're looking for that. Let's call it X. Now the mass of the second isotope, B11, is 11.0093. Now what should be the percentage of the second isotope? Let's think about this. Let's assume that 30% of the boron atoms are B10. If there's only 2 stable boron isotopes, that means that the other 70% has to be B11, because these 2 have to add up to 100. Now, we need to deal with decimal numbers and not percentage base numbers. So 30% is basically 0.3. 70% is 0.7. So if 0.3 is x, we could say that 1 minus x is 0.7, because 1 minus 0.3 will give us 0.7. And that's what you need to understand when dealing with this problem. So if P1 is x, P2 has to be 1 minus x. Now, it's time to do the math. So on the right side, we have 10.0129x, and we need to distribute this number to 1 and negative x. So it's going to be 11.0093 and then minus 11.0093 times x. So let's go ahead and combine like terms. So 10.0129 minus 11.0093, that's going to give us negative 0.9964x. Now our next step is to subtract both sides by 11.0093. So on the right side, this is going to disappear. So this is going to be, let's see, 10.81 minus that number is negative 0.1993, and so that's equal to negative 0.9964x. So let's get rid of some stuff here. I'm just going to rewrite what I have above. Now what we need to do at this point is divide both sides by negative 0.9964. And so this will give us the value of x. Which is 0.2. So P1 was associated with x, and P2 was associated with 1 minus x. Now, if x is 0.20, that means that 1 minus x, which is 1 minus 0.20, that's 0.80. So this tells us that 20% of all of the boron atoms is the B10 isotope, and 80% of all of the boron atoms consist of the B11 isotope. Now, does that answer make sense? Notice that the average is 10.81. The average atomic mass is closer to the mass of the heavier isotope. The reason for that is because we have more of B11 and less of B10. So because B11 is more abundant, the average atomic mass is closer to the mass of the B11 isotope. Now let's move on to part B. In a sample of 600 boron atoms, how many B10 atoms are there? Well, let's find out. So we know that 20% of the boron atoms will be the B10 isotope. So we got to multiply this by 20%. So this is the same as 600 times 0.2. And 600 times 0.2 is 120. So in a sample of 600 boron atoms, 120 out of those 600 boron atoms will be the B10 isotope. In the case of B11, it's 600 times 0.8. And that's going to be 480 B11 atoms. And as you can see, the total adds up to 600. So if you had a sample of, let's say, 1,000 boron atoms, 800 will be B11, and 200 of those 1,000 would be the B10 isotope. Now let's move on to the next problem. Calculate the molar mass of each of the following substances. Well, first we need to know exactly what the molar mass mean. What is molar mass? The molar mass of a substance is the mass in grams of 1 mole of the compound. So let me give you an example. Let's analyze carbon. Carbon has an atomic mass of 12.01. And so what this means is that carbon has a molar mass of 12.01 grams per mole. That's how you could find the molar mass using the periodic table. So if we had 1 mole of carbon, we would have a mass of 12.01 grams. Now you might be wondering, what is a mole? A mole represents a quantity of something. For instance, when you hear the word dozen, what do you think of? A dozen is 12. So if you have a dozen pens, you have 12 pens. If you have a dozen eggs, you have 12 eggs. Well, a mole is like a dozen. It represents a number, a quantity. A mole is 6.022 times 10 to the 23. In this case, 1 mole of carbon atoms is equal to 12.01 grams of carbon. And so the molar mass gives us a conversion factor. It tells us the connection between the quantity of carbon atoms and the mass of carbon. So here is what you need to take from this. When you're looking for the molar mass of a substance, you need to find the atomic mass of the elements involved. And the units will be grams per mole, or you can express it in terms of atomic mass units. But I'm going to use grams per mole. But you're going to find it based on the periodic table, looking at the larger of the two numbers here. So let's work on part A. What is the molar mass of potassium fluoride? So we need to add up the atomic mass of potassium and the atomic mass of fluorine. So you need to get a periodic table and look up the numbers using that table. So the atomic mass of potassium is 39.1 and the atomic mass of fluorine is about 19. So if we add these two numbers, 39.1 plus 19, that's going to give us 58.1. And the units will be grams per mole. So that's how we could find the molar mass of a substance. So what this means is that 1 mole of potassium fluoride has a mass of 58.1 grams. So make sure you understand what is meant by the molar mass. It tells us the mass of the substance if we have 1 mole of that substance. Now let's move on to part B. So let's calculate the molar mass of sodium carbonate. So what we have is 2 sodium atoms, or in this case ions because it is an ionic compound. We have a carbon atom and 3 oxygen atoms. So the atomic mass for sodium is 22.99. And for carbon, it's 12.01 based on the periodic table. And for oxygen is 16. So all we need to do is basically just add these numbers up. So go ahead and type this into your scientific device. So you should get 105.99 grams per mole. And so that's the molar mass of sodium carbonate. So 1 mole of Na2CO3 has a mass of 105.99 grams. Now let's move on to part C. So what is the molar mass of aluminum sulfate? So I'm just going to rewrite the chemical formula so you can see it more clearly. In this formula, we have 2 aluminum atoms. We have 3 sulfur atoms. There is an invisible 1 here if you don't see it. So if it's not there, it's assumed to be 1. So it's basically 1 times this subscript of 3. And that gives us 3 sulfur atoms. Now how many oxygen atoms do we have in this compound? So in this case, it's going to be 4 times 3 because we have 3 sulfate units. And each sulfate carries 4 oxygen atoms. So we have a total of 12 oxygen atoms. Now the atomic mass for aluminum is 26.98. And the atomic mass of sulfur is 32.06. And for oxygen, we know it's 16. So let's go ahead and plug these numbers in and see what answer we get. So I got 342.14 grams per mole. So that's the molar mass of aluminum sulfate. Now let's move on to the next problem. How many moles are in 72 grams of methane? In order to do these problems and those that are coming up next, you need to become proficient at converting units. And for those of you who might need help in this regard, I have another video entitled Converting Units with Conversion Factors. And I'm going to post a link in the description section of this video so you can find it there if you don't want to search it on YouTube. But I recommend watching that video so you can get good at converting units, because every other problem that's going to come after this one, we're going to do a lot of unit conversion. So make sure you understand that topic before moving forward. So let's work on part A. How many moles are in 72 grams of methane? So what we need to do is we need to convert grams to moles. And the only way we can do that is by using the molar mass. So that's the first thing we need to do. We need to find the molar mass of methane. So methane contains 1 carbon atom and 4 hydrogen atoms. Now the atomic mass of carbon is 12.01, and for hydrogen it's 1.008. So let's go ahead and plug these numbers in. So you should get a molar mass of 16.042 grams per mole. Now, what we need to do is take this information and convert it into a conversion factor. So what this means is that 1 mole of methane has a mass of 16.042 grams. So this is our conversion factor. So now what we are going to do is we're going to start with the information that we're given, and that is 72 grams of methane. And we're going to use our conversion factor to convert it from grams to moles. So the conversion factor will be placed in the second fraction. So because we have grams on the top left, we need to make sure that grams of methane will be on the bottom right, so that those units will cancel. And if grams is on the bottom, then moles of methane must go on the top. Now the number that's in front of the moles of methane is a 1, and the number in front of the grams is 16.042. So that's the way we need to set it up. Now we need to divide because we have a number on top and a number on the bottom. If we had 2 numbers on top, then we would multiply. So to get the answer, it's going to be 72 divided by 16.042. And so it's 4.488 moles of methane. So that's how you can convert from grams to moles. Part B. How many grams are present in a sample of 2.5 moles of NO2? So this time we're going backwards. We need to convert from moles to grams. So let's start with what we're given, 2.5 moles of NO2. Now just like before, in the next fraction we need to put the conversion factor. So in order to convert from moles to grams, we need the molar mass of NO2. And so we have 1 nitrogen atom and 2 oxygen atoms. So the atomic mass for N is 14.01 and for oxygen is 16. So 2 times 16, that's 32, plus 14.01. That's going to give us a molar mass of 46.01 grams per mole. So from this, let's write our conversion factor. And that is that 1 mole of nitrogen dioxide contains 46.01 grams of NO2. So this right here is our conversion factor. Now, how should we take this information and how should we place it in this fraction? So looking at the unit on the top left, we have moles of NO2. So we need to make sure that it's on the bottom right. And so on the top, we're going to put grams of NO2. Now the number that's associated with moles is 1, and the number associated with the grams is 46.01. So this time, because we have two numbers that are both on top of the fractions, we need to multiply those two numbers. So it's going to be 2.5 times 46.01. And so the answer is 115.025 grams of NO2. And so that's how you can convert moles to grams. That's how you can set up the conversion process. And make sure that these units cancel. Now let's move on to part C. How many atoms of carbon are present in 7.2 moles of carbon? So in this problem, we need to convert from moles to atoms. If you want to go from moles to atoms or atoms to moles, here's what you need to know. We talked about this earlier. 1 mole of something, it could be atoms, molecules, pens, books, doesn't matter. 1 mole of something is equal to 6.022 times 10 to the 23, which you know it as Avogadro's number. And so this is the conversion that we're going to use to go from moles to atoms. So, as always, let's start with what we're given, and that is 7.2 moles of carbon. Now, what should we write in the next fraction? Since we have moles of carbon on the top left, we're going to put that on the bottom right. So 1 mole of carbon is going to equal 6.022 times 10 to the 23 atoms of carbon. And so make sure you set it up in such a way that the units, moles of carbon, cancel. So what we need to do in this case is we need to multiply 7.2 by Avogadro's number. And so you should get 4.3358 times 10 to the 24 atoms of carbon. And so that's how you can convert from moles to atoms, by using Avogadro's number. Now let's move on to the last part of this question. How many moles are in 4.6 times 10 to the 23 atoms of nickel? So let's start with the information that we're given. Let me write atoms of nickel. When you're converting, there's 3 things that you need. You need the number, you need the unit, it could be grams, moles, atoms, molecules, and you need the substance. Right now, in the problems that we're dealing with, we're only changing the unit. Of course, we get a different number, of course, but we haven't changed the substance yet. In other problems, that's going to be something you need to be aware of. So not only do you need to convert the unit, you may need to convert from one substance to another. So just keep that in mind. So once again, we're going to use the same conversion. 1 mole is equal to 6.022 times 10 to the 23. So this time, I need the unit atoms on the bottom. So I can say that there's 6.022 times 10 to the 23 atoms of nickel for every 1 mole of nickel. because what's on the top must equal what's on the bottom in the conversion fraction. So these units will cancel, and now we're going to get what's left over, the unit on the top, that is moles of nickel. So this time, because we have a number on the top and one on the bottom, we need to divide instead of multiplying. So it's 4.6 times 10 to the 23 divided by 6.022 times 10 to the 23. And so you should get 0.7639 if you round it, moles of nickel. And so that's it for this problem. Now let's consider number 5. How many atoms of iron are in a sample of 235 grams of Fe? So in this problem, we need to convert from grams to atoms, but we can't do so directly. What we need to do is convert from grams to moles. We know how to do that using the molar mass. And then once we have the number of moles, we could use Avogadro's number to convert to atoms. So this is a multi-step process. Now the first thing we need to do is look up the molar mass of Fe. So using the periodic table, you should get 55.85 grams per mole. So what this tells us is that 1 mole of Fe is equal to 55.85 grams of Fe. So this is our first conversion factor that we need to use. The second one is just Avogadro's number. We know that 1 mole of Fe contains 6.022 times 10 to the 23 atoms of Fe. So let's begin. Always start with what you're given. In this case, 235 grams of Fe. Now, let's use the first conversion factor to convert it from grams to moles. So we need to put grams on the bottom. 1 mole of Fe has a mass of 55.85 grams of Fe. So we could cancel the unit grams of Fe. Now the next thing that we need to do is use the last conversion factor. We need to convert from moles to atoms. So since we have moles on the top, let's put it on the bottom. So 1 mole of Fe contains 6.022 times 10 to the 23 atoms of Fe. So now, let's perform the calculation. So what we're going to do first is we're going to take 235 and divide it by 55.85. Go ahead and type that in. So you should get, at this point, 4.2077. And then take that result and multiply it by this number. So the final answer that I got is 2.53 times 10 to the 24 atoms of Fe. And so that's it for this problem. That's how you can convert from grams to atoms without changing the substance. Now, if you look at part B, the substance is going to change. Part A and part B are similar because we're given the grams of this substance. That could be glucose or fructose, C6H12O6, and we want to convert it to the atoms of carbon. So both in part A and part B, we're going from grams to atoms. But let me show you the difference between the two, because when you're working out these problems, you need to pay attention for this. So in part A, we've converted the grams of Fe to the atoms of Fe. And in part B, what we need to do is go from the grams of, let's say, glucose to the atoms of carbon. So the difference between part A and part B is that in part A, the substance is not changing. However, in part B, we need to change the substance. So part B requires an extra step relative to part A. So let's begin. Well, first, let's write out a map of what we need to do, or an outline. So we're going to start with the grams of C6H12O6. And then, using the molar mass, we're going to convert it to moles. And then once we have the moles, what we could do is convert it to the atoms of glucose. And then once we have that, now we need to change the substance. So we're going to convert glucose into carbon. So the first step, we need to use the molar mass. For the second step, Avogadro's number. For the third step, we need to use the formula that we have here. So let's go ahead and begin. So let's start with what we're given, and that is 356 grams of glucose or fructose. They have the same molecular formula. Now let's convert it to moles. So we need the molar mass. We have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So the atomic mass of carbon is 12.01, and for hydrogen it's 1.008, and for oxygen it's 16. So let's go ahead and type this in. So you should get 180.156 grams per mole. So what this means, let me see if I can use less space, is that 1 mole of glucose has a mass of 180.156 grams. Now we could cancel grams and glucose. So now let's use Avogadro's number. So let's use the fact that 1 mole is equal to 6.022 times 10 to the 23. So we could say 1 mole of glucose has 6.022 times 10 to the 23. Now we can't say atoms because C6H12O6, that entire particle, is not an atom, but rather it's a molecule. A molecule is a particle that it's made up of many atoms. So we need to say we have this many molecules of glucose. Let's see if I can fit it in here. I'm running out of space. So now we could cancel the unit moles of glucose. Now the last step, to change the substance, we need to use the chemical formula of glucose. In other problems later in this video, we could use the coefficients of a balanced chemical equation to change the substance. And we'll talk more about that later. But for now, we need to use the formula of glucose, which is C6H12O6. So according to this formula, we could say that 1 molecule of glucose contains 6 atoms of carbon. Do you agree with that? So this is our conversion factor for the last step. So since we have molecules on the top, we need to put it on the bottom. So I could say that 1 molecule of glucose contains 6 atoms of carbon. So now every unit has been canceled except the unit that we want to get, which is atoms of carbon. So now we just got to do the math. So it's going to be 356 divided by 180.156. Take that result and then multiply it by Avogadro's number, and then multiply that by 6. So the final answer that I have is 7.14 times 10 to the 24 atoms of carbon. So that's how you can go from the grams of, let's say, substance A to the atoms of substance B. Now let's move on to part C. What is the mass of a sample in grams that contains 3.5 times 10 to the 24 molecules of SO3? So as always, let's start with what we're given. And let's plan out what we need to do. So we just need to find the mass of the sample. So right now we have molecules of SO3. SO3 is a molecule. It's consistent of, it's made up of many atoms. So once we have molecules, using Avogadro's number, we can convert from molecules to moles, and then using the molar mass, we can go to grams of SO3. Now we don't need to do anything else, because once we have the mass in grams, that's it, we're done. So we don't have to change the substance in this example. So using Avogadro's number, we could say that there's 6.022 times 10 to the 23 molecules of SO3 for every 1 mole of SO3. So we could cancel these units. And now for the last step, which I'm going to rewrite here, we need the molar mass. So we have 1 sulfur atom and 3 oxygen atoms. Sulfur has an atomic mass of 32.06, and for oxygen is just 16. And so you should get 80.06 grams per mole. So what this means is that 1 mole of sulfur trioxide has a mass of 80.06 grams. And so since we had the unit moles of SO3 on the top left, in the third fraction it has to be on the bottom right so that they will cancel. And now let's perform the calculations. So it's going to be this number, 3.5 times 10 to the 24 divided by Avogadro's number. And right now you should have like 5.812, and then we're going to multiply it by 80.06. And so the final answer is 465.3 grams of SO3. And so that's it for this example. Now let's move on to part D, the last part of this problem. Calculate the mass in grams of a sample of silicon tetrafluoride that contains 2.8 times 10 to the 23 atoms of fluorine. I know I marked over it, but that's atoms of fluorine. Feel free to pause the video if you want to try this problem. So we're given the atoms of fluorine, and we need to convert it to molecules of SiF4. So first, let's go from atoms to molecules. And we're going to change the substance. And then we're going to go from molecules to moles using Avogadro's number. And then using the molar mass, we're going to go from moles to grams. So it's helpful if you can write out like an outline of what you need to do with regard to your conversion process. So let's start with what we're given. 2.8 times 10 to the 23 atoms of fluorine. Now, in silicon tetrafluoride, we can say that there's 4 atoms of fluorine for every 1 molecule of silicon tetrafluoride. So this is the conversion factor for the next step. And so I need to put the atoms of fluorine on the bottom. And on top, 1 molecule of SiF4. So I could cancel these units, atoms of fluorine. Now the next conversion factor that we need is this one. We could say that 1 mole of silicon tetrafluoride contains 6.022 times 10 to the 23 molecules of silicon tetrafluoride. So I need to put this part on the bottom. And so I could cancel these units. And on top of the third fraction, I'm going to write 1 mole of silicon tetrafluoride. Now the last step is to convert from moles to grams. And so I need the periodic table for that. So in SiF4, I have 1 silicon atom and 4 fluorine atoms. Silicon has an atomic mass of 28.09, and fluorine has an atomic mass of 19. And so if we add these values, this will give us 104.09 grams per mole. So what we can write in the next fraction is that 1 mole of silicon tetrafluoride has a mass of 104.09 grams. And so now we could cancel the unit moles of SiF4. So to do the math, it's going to be this number divided by 4, which is 7 times 10 to the 22. Take that result, divide it by Avogadro's number. And right now you should have 0.116, and then multiply it by 104.09. So the answer that I have is approximately 12.1 grams of silicon tetrafluoride. And so that's it for this problem. So now you know how to go from grams to atoms and atoms to grams, and at the same time changing the substance from one element into a compound. Number 6. Calculate the mass of 25 carbon atoms in AMU, or atomic mass units, and in grams. So what do you think we need to do in this problem? How can we get the answer? Well, first let's calculate the answer in AMU. Now, using the periodic table, you'll find that the atomic mass of carbon is this number on the bottom, 12.01. So we can write a conversion factor. We could say that 1 carbon atom has a mass of 12.01 AMU, atomic mass units. So if that's the case, how many atomic mass units are present in 25 carbon atoms? So we're going to set it up as a conversion problem. So we're going to start with what we're given, 25 carbon atoms, and then use this to convert it to AMU. So each carbon atom has a mass of 12.01 AMU. And so we could see the units carbon atoms cancels. And so it's just going to be 25 times 12.01. So the answer for the first part of the problem is 300.25 AMU. Now let's convert this to grams. Another conversion factor that you want to know is that 1 gram is equal to 6.022 times 10 to the 23 atomic mass units. So what we could do is start with 300.25 AMU, and then in the next fraction, we could say that 1 gram is equal to this many atomic mass units. And so AMU will cancel, and it's just going to be 300.25 divided by Avogadro's number. And so this will give us this answer, 4.986 times 10 to the negative 22 grams. And so that's how you can convert from atomic mass units to grams. Now, another way in which you could have done this problem, let's say if you just want to go from atoms to grams, you could start with 25 carbon atoms, and then using Avogadro's number, you can convert it to moles. So 1 mole of carbon is equal to 6.022 times 10 to the 23 atoms of carbon. So we could cancel these units. And then we have the molar mass of carbon. 1 mole of carbon has a mass of 12.01 grams. And so this will give us the same answer. And that is 4.986 times 10 to the negative 22 grams of carbon. So as you can see, there's different ways in which you can arrive at the same answer. Number 7. Calculate the percent composition by mass of each element in the compound C6H12O6. So how do we find the mass percent of an element in a compound? Here's the formula that you need to know. So let's say we want to find the percent by mass of the element carbon. What we need to do is take the mass of carbon, this could be just the molar mass of carbon, and divide it by the total mass, or the total molar mass, of the compound, which is C6H12O6. And then we're going to multiply that by 100%. And so that's how you find the mass percent of an element in a compound. It's just the mass of that element divided by the mass of the compound times 100%. So if you want to try this problem, feel free to pause the video and work on it yourself. And then you could play the video again and see if you got the right answer. So let's start with carbon. The molar mass of carbon is 12.01. Now in this compound we have 6 carbon atoms. So we need to multiply the molar mass by 6. Now on the bottom, we're going to put the total molar mass, the total molar mass of the entire compound. And so that's 6 carbon atoms plus 12 hydrogen atoms, where each hydrogen atom has an atomic mass of 1.008. And then we have the 6 oxygen atoms. And then we're going to multiply this whole thing by 100%. So 6 times 12.01, that is 72.06. Now I'm going to type in this whole thing. And let's see what I'm going to get. So the molar mass for the entire compound, that is glucose or fructose, is 180.156. And the units, grams per mole, or you could say atomic mass units. Now remember this number because we're going to use it when calculating the mass percent of hydrogen and of oxygen later in this problem. So 72.06 divided by 180.156 times 100%. So that gives me 39.999%, which I'm going to round it and say it's about 40%. So that's the mass percent of carbon in this compound. Now what about the mass percent of hydrogen? So what we're going to do is take the total mass of hydrogen. So we have 12 hydrogen atoms, each with an atomic mass of 1.008, and then we're going to divide it by the molar mass of the compound, which is 180.156, and then multiply everything by 100%. And so you should get 6.714%. So I'm going to round that and say it's 6.7%. Now the last one is oxygen. So in the compound C6H12O6, there's 6 oxygen atoms, each with an atomic mass of 16. And once again, we're going to divide it by the total molar mass of the compound, which is 180.156, and then multiply it by 100%. The answer that I got is 53.3%. So that is the mass percent of oxygen. Now, notice that if you add up these three numbers, you should get 100%. That has to be the total. Anytime you're calculating the percent by mass of every element in a compound, it should all add up to 100. If it doesn't, that means somewhere along the lines there's a mistake and you need to look for it. So that's it for this problem. Now you know how to calculate the mass percent of an element in a compound.